So it's a great pleasure to have Zhuoran Yang presenting today about provably efficient exploration in policy optimization. Zhuoran is from Princeton University. I think he's fifth year PhD student there. And he did his undergrad at Qi Cai before. And he's known as maybe one of the most prolific recent PhD students working on RL theory, at least to me. So he showed up on the horizon a couple of years ago, and he keeps producing really interesting papers that I'm always eager to read about RL, function approximation, I don't know, exploration, intersection with statistics, neural networks, everything. So it's a great pleasure to have him. Zhuoran, stage is yours.
Okay, thank you. Thank you, Chaba and Kiara, for the kind introduction. I would like to thank the organizers for putting up such a great seminar series for reinforcement learning researchers during this pandemic. And this is a joint work with Qi Cai and Professor Zhaoran Wang from Northwestern University and Professor Qi Jin from Princeton University. In recent years, we have witnessed the great empirical success of deep reinforcement learning in real world. Combining deep learning tools and big data and computational resources, reinforcement learning have tackled many complicated sequential decision-making problems that are once perceived as too complicated to tackle by a machine. And the most popular applications are in the realm of games, starting from single-agent Atari games to two-player zero-sum games such as Go, and to multi-agent partial information games such as poker and StarCraft 2. Also, recently, OpenAI has used deep reinforcement learning algorithms to train a real robotic hand to solve the Rubik's Cube. And Google also utilized deep reinforcement learning to solve a problem related to artificial general intelligence, such as designing how to place, such as the chip placement problem. And interestingly, in those success stories, AlphaGo and StarCraft 2, Rubik's Cube, and even the chip placement, the driving force is the policy-based optimization, such as actor critic and proximal policy optimization. And however, deep reinforcement learning is not the panacea for all the decision-making problems. It suffers from both computational and statistical challenges. In terms of computation, in practice, it is often observed that deep reinforcement learning algorithms fail to converge. And even if it converges, the policy found by the reinforcement learning algorithm might not be very good. It might perform roughly the same as a randomized policy. And on the statistical side, deep reinforcement learning requires a huge amount of data to make it work. As an example, in AlphaGo, the researchers utilize 29 million games of self-play, and this huge amount of data takes 40 days for the training to complete. And due to the sample inefficiency, such a sample inefficiency also in turn causes additional challenge on the computational side. Because we have such huge amount of data, it takes a very long time to complete the training process. And if we don't get satisfied results, then we need to further fine-tune the hyperparameter of the neural network and go through the pipeline again. So that will be very cumbersome. And such a huge amount of data requirement and computational resources prohibits individual researchers and small companies from applying reinforcement learning algorithms in practice. And also in problems in critical domains such as healthcare, we need to ensure that the algorithm is stable enough. Otherwise, the failure will have a detrimental effect. And in our goal, in this paper, our goal is to understand the computational and the statistical efficiency of policy optimization from a theoretical perspective. And I think our audience are quite familiar with with the model of reinforcement learning. So in the following 3 slides, I will basically briefly introduce the setting of reinforcement learning to make sure that we know we set the same notation system. Here, we consider the episodic Markov decision process as the model of reinforcement learning. So in such a model, the agent interacts with the environment for a total of h steps. And for simplicity, we assume that the initial state S1 is fixed to a particular state as star. And starting from this initial state, in each step, the agent takes an action and gets a reward. And then the system evolves into a new state according to the Markov transition kernel. Here, the policy, because we have in total h steps, any policy is just a set of h different functions where each one corresponds to a single, how to take action in a single step. And after this episode ends, when the last state sh is achieved, the agent collects his or her reward, which is the sum of the h total rewards. And a critical notion is called the value function, which is for any policy pi, VH pi just denotes the expected total return starting from SH and following policy pi afterwards. Then by this definition, the total return obtained by following policy pi is just equal to the V1 pi evaluated as the initial state as star. Another related notion is called the Q function or action value function associated with the policy pi. It's defined as the expected total return when we conditioning on the fact that we start from conditioning on the fact that the state action pair in the h step is fixed to a particular state action pair S and A. Then these two kinds of value functions are closely related by the Bellman equation. Because we consider the episodic case, we don't have any reward after the h step. That means V capital H plus 1 is equal to 0. Then going backwardly, we can build the relationship between the Q function and the V function. In specific, Q function is equal to the sum of the immediate reward plus a one-step look ahead given by the Markov transition kernel. And the V function can also be obtained from the Q function by taking the inner product between the Q function and the policy. To study policy optimization and sample efficiency, we consider the online setting where the agent interacts with the environment and plays the episodic MDP repeatedly. We assume that the agent plays such an episodic MDP for T episodes. And each episode, within each episode, the agent just starts from the fixed initial state and execute its policy. The policy in the Tth episode is denoted by pi t, where the superscript t here stands for the number of episodes, and the subscript h corresponds to the step within each episode. So after t total number of episodes, the number of data obtained by the agent is just equal to capital H multiplied by capital T, because we have in total T episodes and there are H data points within each episode. And to measure the sample complexity, we need to define a performance metric, which is called regret. Here, the agent aims to learn the optimal policy, which is denoted by pi star, using the total T multiplied by H data points. And the optimal policy is defined as the maximizer of the expected total return. And to quantify the sample complexity, we compare the sequence of policies generated by the agent against the optimal policy, and the difference between these the expected return obtained by a policy pi and the expected return obtained by the optimal policy is just a suboptimality of the policy pi, and the regret is defined as the cumulative sum of all these suboptimality terms. And to study the sample efficiency of reinforcement learning, recently there have been many interesting works in this direction, and specifically for the functional approximation setting. And I think we have heard Chijin and Cheyu and Andrea talking about their research on value-based reinforcement learning algorithms with linear function approximation. And recently, there are also several works studying general function approximation, including a recent work by Alex and Chaba and Lin and other collaborators. And in terms, and all these works, this is a very partial list of related work, and all of these work consider value-based methods or model-based UCRL type of algorithms, which is a different class from the policy-based optimization. In terms of the computational efficiency of policy optimization, there is also another line of research assuming, considering the convergence and optimality of policy-based optimization algorithms such as natural policy gradient and proximal policy optimization. And most of these work consider tabular or linear settings or over-parameterized neural network. And these works also only consider the computational aspects, assuming we have the model, we have the transition model, or we can sample from a fixed distribution that is well explored. In terms of to address the exploration aspect or the sample efficiency of policy optimization in the online setting, there are also heuristic methods that combines policy-based optimization with exploration. These methods include random network distillation, pseudo counts, or adding intrinsic rewards. However, these works are mostly heuristic, and we don't have a good understanding of the theoretical aspects of these works. And to be more specific, in this work, our goal consists of two steps. Consists of two aspects. The first aspect is we want to design a policy-based optimization algorithm that address the exploration versus exploitation trade-off in a principled manner. And for such an algorithm, the second question is to understand its convergence and optimality and sample efficiency. To assess the sample efficiency, we consider the regret bound, and we hope to achieve a sublinear regret. That is, the regret scales with t in terms of small t, and moreover, we want the regret bound to scale with the size of the problem in terms of polynomial of h and polynomial of the intrinsic dimension. So this problem faces the dual challenges from the computational side and the statistical side. In terms of computation, the challenge is that policy optimization is generally a non-convex problem. Moreover, we need to incorporate function approximation. Hopefully, we want to incorporate nonlinear function approximation, such as neural networks, into the policy-based optimization algorithm, which further exacerbates the computational challenge. In terms of statistical challenge, because we are in the online setting, we need to actively decide which action we want to take. So the data acquisition process is active, and thus the data are not IID. Moreover, these two types of challenges are coupled with each other because we need to because the statistical estimation problem is embedded into a optimization problem, namely the policy optimization. So the statistical error will be propagated along the optimization algorithm, which means that these two types of challenges are intertwined with each other. And the algorithm we study is a meta-algorithm called Proximal Policy Optimization, which is proposed by Zhang Schumann et al. in 2017. And this algorithm consists of 2 steps. It's an iterative algorithm, and within each iteration, there are 2 steps. The first step is a policy evaluation. That is, given after the teeth episode, when we have data executed from PyT, we want to compute the action value function associated with the policy executed in the teeth episode. This is called policy evaluation problem. Here, in this formula, we assume that we know exactly what the model is. Then we can compute this action value function using Bellman equation we introduced. So after obtaining this value function, the next step is to obtain a new policy. This is achieved by a regularized policy improvement step. Here, the regularization term is a KL divergence, and the subsize alpha is the subsize. We use the action value function Q function as the descent direction. So this problem has closed form solution, and the solution separates for each individual state. And moreover, because we add a KL regularization problem, this corresponds to a mirror descent step, where the primal variable is just a policy, and the dual variable is a value function, also called critic. And by having a finite step size and mirror descent step, the policy update is we ensure that the solution PyT plus 1 is rather close to the last iterate PyT, which enables us to have a stable policy sequence. And more specifically, this algorithm is closely related to conservative policy optimization or natural policy gradient due to the close connection between KL divergence and Fisher information. It's also related to policy iteration. Suppose we drop the regularization term, then the new policy will just be the greedy policy with respect to Q pi t, which recovers the classical policy iteration algorithm. And to understand the computational or the optimization aspect of this population version of PPO, we utilize the famous performance difference lemma proposed by Kakaday and Lanford in roughly 20 years ago. This lemma characterizes the difference between the suboptimality of any policy pi against the optimal policy. And this lemma shows that the suboptimality term can be written as roughly as the inner product between the Q function and the policy difference. So this can be viewed as a Taylor expansion in the policy space from the functional perspective. And the dual variable or the critic can be viewed as a gradient. And moreover, because pi star is the optimal policy, this term is always non-negative. That means from the functional perspective, this performance difference lemma gave us the geometry at the optimal point, pi star. That is, at the optimal policy, roughly speaking, the expected total return as a functional of the policy is convex or one-point monotone. So as shown in this figure, this geometry shows that the the direction pointing from the current policy pi to the optimal policy pi star forms an acute angle between the descent direction q pi. Then when we update the policy pi following this descent direction, although this is not exactly the policy gradient, we can still make some progress, and eventually it will converge to the optimal policy. And we can show that this algorithm population version of PPO converges in a sublinear rate to the optimal policy, and the regret is bounded scales with t in terms of square root of t. Actually, the proof is very simple. It's just a combination of the analysis of one-step descent and the performance difference lemma. So this is the one-step descent. The characterization of one-step descent follows from the convex optimization literature. If we can bound this, the pairing between the dual variable and the policy difference by a sum of two terms, where the second term corresponds to the decrease in terms of the Bregman divergence, and the first term corresponds to, roughly speaking, corresponds to the norm of the squared norm of the gradient. And then we utilize the performance difference lemma to write the regret as a sum, as a telescoping sum of those one-step descent terms. And then, luckily, the KL divergence cancels with each other, and the only KL divergence left is the initial one. And when we initialize our policy using a uniform policy, that is taking actions, all the actions uniformly, this term will be bounded by a constant. And finally, we choose a step size that balance these two terms and get a square root of t regret.
Sorry, can I have a quick question? Or I don't know if this is an appropriate question, but so this has been done before several times in different papers, right? So this algorithm that you outlined, this is pretty much the MDP expert algorithm. I don't know if you're going to discuss this later.
Yeah, MDP.
Right, yeah, MDP, right? So there, the idea is, well, to reduce the regret of the global algorithm to these localized regrets that you wrote in the previous slide.
Yeah.
And in that sense, so I'm just curious about what's so specific about this analysis that you present here. Could you use like any other expert algorithm and get the same result essentially?
Yes, I think we can use other algorithms such as following the perturbed leader or following the randomized leader or polytax. So the reason why I introduced this is because the OPAL algorithm utilized this fact, and this similar analysis, as we will see later, it will also pops up in the analysis of OPAL.
Right, and is that going to be specific to the KL divergence, or even there in OPAL you could use something else?
Well,
yeah, maybe we can discuss this later, because this is a very, very deep rabbit hole, I suppose.
Okay.
All right, so I'll
keep going.
Thank you.
Okay. So previously, I assume that the model is known, but if we go out of our comfort zone and in the real world, we don't know the transition model. So we need to, that means we don't directly have the critic Q pi. Then we need to estimate this from the data. And so in practice, what PPO does is to first estimate the critic from the data, and then plug the estimated critic into the KL regularized policy improvement step. And this estimated critic can be achieved by various policy evaluation algorithms, such as LSTD or GTD, etc. And in terms of theory, this method still works if we can have some bound on the policy evaluation error. Suppose we can have the control of the error in terms of some norm, and this norm is small for all t, then we can use Holder's inequality to quantify the effect of policy evaluation error and still get the global convergence. However, to ensure that we can have a uniform control of the policy evaluation error, that is, in terms of certain norm, we need the data distribution to be rather regular, which is, in theory, it's achieved by, say, assuming we have a generative model to sample from, or the sampling distribution has a density that is lower bounded. That being said, designing such a good sampling distribution nu itself hides the challenge of exploration. And how to design this distribution, this sampling distribution, reflects the fundamental trade-off between exploration and exploitation, as we will see in this example. In this example is the famous combination lock counterexample. And we assume there are, so the state space is 100. There are 100 total states, and the initial state is the leftmost one, x1. And there are two types of actions, either going to the right or going to the left. If you choose to turn to the left, then you will jump to the previous states uniformly. For example, at x4, you can either go to the right, jump to the x5, or if you choose to turn left, then you will go to x1, x2, x3 uniformly random. Then in this MDP, you only see the reward if you reach the last state, x100, and if this state is reached, you will stay there forever. So in this MDP, because we start from the leftmost state, x1, and there are high probability of jumping backwardly if we choose to turn left, then a bad data distribution will never achieve this rightmost state, x100. That means in the data we collected, we don't see any reward. Then if we use that data set to solve a policy evaluation problem, the estimated critic will be roughly 0 for all policy. Then if we plug in that estimator into the policy optimization algorithm, the PPO will not make any progress because the descent direction is just meaningless. And this happens because we cannot have a uniform control over the policy evaluation error. So this example shows that in policy optimization, still exploration is the key for achieving sample efficiency. So this motivates us. This motivates our optimistic PPO algorithm. In our algorithm, because having a uniform control over the policy evaluation error is impossible, instead we want to we propose to have a crude estimator, have an initial estimator Q hat of the critic action value function, and then we would like to assess the uncertainty of this initial estimator by constructing a non-uniform uncertainty quantification. That is, we want to have a pointwise confidence interval of the estimated value function. So here, this gamma corresponds to the width of the confidence interval. And this is a non-uniform confidence interval because here this gamma itself is a function. And then what we propose is that we do not use the x hat as the descent direction. Instead, we construct another descent direction function, QHT, which is the sum of the initial estimator plus the confidence, the width of the confidence interval. That is, in other words, we want to compensate for the uncertainty of the estimator. Then what we do is to utilize this Q function as a descent direction and plug it into the standard PPO update. And because we first construct a confidence interval and then we compensate for such an uncertainty, the obtained Q function, QHT, is always an upper bound on the population version of the critic. So that recovers the principle of optimism in the face of uncertainty. That is the reason why we call this algorithm OPAL, because we combine PPO with an optimistic policy evaluation. And this algorithm, this general algorithm framework does not depend on the specific function parameterization form, as long as we can have a pointwise confidence interval, we can utilize this algorithm. And how to construct, what I haven't talked about is how to construct the initial estimator and the confidence interval. So in the following 2 slides, I will first focus on the linear function approximation setting as a concrete example to illustrate the idea. Suppose we have a linear kernel MDP. That is, the transition kernel can be written as a linear function of a known feature function. And this feature mapping phi is a known function which maps each tuple to a d-dimensional to a vector in the d-dimensional Euclidean space. And we assume the transition kernel has a true parameter theta h star. And then because we have a linear kernel, because the transition kernel is linear for any value function v, the p theta v is also a linear function in theta, and the basis now can be computed by the original feature mapping phi and the value function v. Then we can estimate the true parameter using ridge regression, which corresponds to a method of moments. Here, the response variable is just equal to the value function of the next state, of the next step, and the covariate is a feature computed by the value function as well as the current data. And here, the lambda is a regularization parameter. And in other words, we use these two type of data to construct an estimator of the model parameter. And this linear kernel MDP covers the tabular case if we set the basis function to be the canonical basis. And in that case, the dimension d is just equal to s squared multiplied by a. And once we have an initial estimator of the model parameter, we can construct the initial estimator of the Q function using Bellman equation. So we can go backwardly, starting from the last value function being 0, because we don't have any rewards after the h time step. And starting from here, we go backwardly and use the estimated, use the Bellman equation associated with the estimated model theta hat. And then after having this estimator, we compensate for the randomness of the estimator theta hat, which is denoted by this gamma function. This is essentially it quantifies the uncertainty of the parameter theta hat. Then we construct the descent direction by adding this Q hat function and the confidence interval. And then we obtain the value function v similarly as in the Bellman equation. Intuitively, well, in the tabular case, intuitively this confidence interval reduces to the count-based uncertainty, count-based UCB bonus. And for the linear case, this is also similar to the one designed for linear UCB. And we also have a Bayesian perspective to view this bonus function. Suppose, as I introduced, we estimate the theta, the parameter of the MDP using ridge linear regression, which is similar to a Bayesian linear regression with a Gaussian prior. So here we can regard theta h star, this true parameter, as a random variable with a Gaussian prior. Then this bonus function can be viewed as an information gain, a condition on the historical data up to time t, and we have an additional data point as an A. So in other words, this term information gain is reduced to the reduced entropy when we have an additional state action pair given the historical data up to time t. And the bonus function just corresponds to the square root of the information gain. So I just talked about how to construct the decent direction in the linear kernel MDP. So suppose we can also do similar things for a general parametric model. Suppose here the model has a parametric form, and which is not necessarily linear. Here we can still use method of moments plus a regularization to estimate the model parameter. And this is similar to a recent paper done by Alex and Chaba and Lin for general function approximation. And using this estimated model, we can similarly obtain a decent direction by iterating over the Bellman equation and also add an uncertainty quantification term to ensure optimism. And we can similarly obtain the V function. And combining these two, we can plug in this decent direction into the PPO algorithm and obtain the next policy, iterate. So in terms of theory, we show that for the linear under the linear setting, if we set the regularization parameters equal to 1 and set the subset alpha properly, our OPAL algorithm achieves sublinear regret. And that is, it depends on t through square root of t. And also it depends on the size of the problem through d multiplied by h squared. H is the length of the episode, and d is the dimension of the feature. And our algorithm can also be readily extended to the kernel setting. The only thing need to be changed is we just need to change this dimension d into the effective dimension of the RKHS, which is defined through the eigenvalue decay. This regret bound also translates to a sample complexity bound with constant probability for achieving any epsilon suboptimality. That is, with this number of samples, we can find a policy whose performance is just epsilon inferior compared with the optimal policy. And also, the linear setting covers the tabular setting as a special case, then it also implies a square root of t regret under the tabular setting. And in a concurrent work, Efroni et al. Also established a similar regret in the tabular setting, but they directly estimate the tabular transition model, so they have a slightly better dependency in terms of S. And our regret bound also, this regret bound for OPAL also matches the regret bounds for value-based algorithms such as LSVI and UCRL analyzed in Alex Chaba and Lin's recent work. So as I just said, our OPAL achieves the same regret as LSVI. Then that begs the question, what is the advantage of using a policy-based optimization? So to address this, we can consider the adversarial reward setting. That is, in each episode, the reward function might change. Here in t-th episode, we denote the reward function is given by RT, which changes as t increases. Also, we consider the full information feedback setting. That is after before the starting point of the t-th episode. The agent does not know the reward function, and it specifies his or her action. And after the termination of this very episode, it observes the reward function. And in this adversarial reward setting, the benchmark is a policy which achieves best in the hindsight performance. That is, it maximizes the cumulative reward across all the total T episodes. And interestingly, we show that our OPAL algorithm, the very same algorithm under this adversarial setting, achieves a similar sublinear regret. And the reason is by adding a KL regularization term, which is absent in the value-based methods, we ensure that the policy sequence remain close with each other, and that means the policy sequence remains stable. And also, we add optimism to achieve sample complexity. So the take-home message is that under such a non-stationary world, KL regularization and optimism combined together is robust to the adversarial reward. And in terms of how to prove the sample efficiency, we show that in our proof we show that optimism actually is the key. By achieving, recall that our descent direction, this guy is an upper bound of the population version of the critic. So by having such an optimism, actually the regret bound can be upper bounded by a sum of computational error and the statistical error and the martingale difference term. This term, martingale difference term, is a minor term that doesn't matter. And here the interesting fact is that by having such an optimism, we actually disentangle the computational and statistical error, and we can analyze these two components separately. And the analysis of computational error is just exactly the same as the population version of PPO algorithm. So this guy, this computational error illustrates the convergence of the algorithm, assuming we know exactly what the transition model is. And the statistical error part consists of the total price paid for achieving optimism on the past historical data. And this regret decomposition actually is not limited to policy-based optimization. It also holds for value-based algorithm. Just suppose we consider the value iteration algorithm, then this guy will just be equal to 0 because the new policy is always a greedy policy with respect to the descent direction. And also this is also, so when the model is known, for value iteration algorithm, the computation error is exactly 0 because when the model is known, we can just compute the Bellman equation to get the optimal policy. And so this term reflects the computational cost of the reinforcement learning algorithm when we know the model. And this term also shows up for the analysis of value iteration algorithm. It corresponds to the total amount of statistical price paid for achieving optimism. And to handle these three terms, the martingale difference can be handled using standard concentration tools. And the computational error can be handled, as I just introduced, using the mirror descent analysis and performance difference lemma. And the statistical error, because the bonus function is proportional to the square root of the information gain, we can bound this telescoping sum using Cauchy-Schwarz inequality, and then the sum of the information gains cancel with each other, and which gives us a sublinear regret. As a summary, in this work, we address two problems. First, we propose a principled algorithm named OPAL, which achieves sample efficiency in the online environment. And the key feature of this algorithm is that we use a KL regularized policy improvement step combined with optimistic policy evaluation subroutine, where the solution to this subroutine serves as a descent direction. And this algorithm achieves both global optimality and sample efficiency in the online setting with a sublinear regret. And moreover, the feature one key feature that differentiates OPAL from value-based methods is that it can be robust to adversarial reward functions by compared with the bias in hindsight policy. In terms of future research, we would like to extend it to general function approximations such as RKHS or neural networks, and also we would like to handle bandit feedbacks, especially in the adversarial reward setting. And also we would like to extend it to the competitive reinforcement learning settings such as zero-sum games. And currently we have some initial results for games where the transition model, the transition dynamics is controlled by one of the players. And that concludes my talk. Thank you all very much.
All right, thanks very much.
Thank you.
There we go. Nice. Well, thanks so much. So I have like a number of questions here. Some of those are related to the ones that I asked earlier. As in, could you use other regret minimization algorithms and still get the same result, even with this exploration bonus that you're using, or somehow the KL divergence and the exploration bonus that you use somehow need to work together?
This is a very great question, actually. I haven't given much thought about this, but I think it's possible to use other regularization as long as you can telescope those fragment divergence together. I think Professor Haipeng Luo has one of the paper that uses a different fragment divergence called log barrier or something. Yeah, and also in one algorithm called regret matching utilize another fragment divergence, and they can also telescope. So I think the answer might be yes.
Yeah. That feels like the right answer to me as well. So and regarding the result, so you were talking about these linear kernel MDPs, and so your results really only hold for these and not for linear MDPs?
Oh, it only holds for linear kernel MDP, not the linear MDP. The reason is, as I talked with Chaba, in term for linear MDP, we have some trouble bounding the covering number of the estimated value function, because here we need to cover the policy class as well, because the policy here is random, it's no longer greedy, and surprisingly the policy class is large, and currently we don't have any good method to bound this.
Right. Yeah. I understand. Okay, that's a very great point.
Can you explain a little bit more? Maybe it's not so obvious for everyone how the greediness would have in bounding the covering numbers.
How the greediness?
Yeah, like you said that the policies here are stochastic, and that represents an extra challenge as opposed to having just greedy policies.
Yeah.
Which would be deterministic normally. So is it really the stochasticity, or is it like beyond stochasticity there is something that's going on, and stochasticity just adds on the top of things? Is it clear what I'm?
Yes. So here, our algorithm, because we use KL regularization, they obtain. Let me find out the closed form solution. So here, as we can see, this policy optimization has a closed form solution, and then if we expand this term, we can write the policy as an exponential, where inside of this exponential is a sum of a bunch of Q functions. That means this policy is stochastic. But in contrast, in LSVI, we always make the policy, the greedy policy, with respect to the last Q function. So in the algorithm analysis, we need to cover. So in the LSVI proof, we need to cover a uniform concentration and over the class of all value functions obtained in the algorithm. So here the value function class is just equal to all those QHK, the inner product between those QHK and the PyHK, or the VHK, the value function where the function VHK belongs to.
Yeah, right. I think I understand this point, but still, I think that in that LSVI UCB analysis, so I think there the requirement that you have is that the value function is somehow smoothly parametrized in terms of some low-dimensional parameter vector. And I think that this is still the case here, right?
Yeah.
So that you replace the max with a softmax, but eventually you're still smooth in terms of like a linear term plus some nonlinear exploration bonus.
Yeah, here it's we consider the model-based approach. Then the covering number would be, we only need to cover the class of this guy, this PV. But in the model-free case, we need to cover the class where this V function belongs to. That's more complicated because in the framework of linear MDP, it's assumed that the Q pi is linear. Then that means this guy will actually not be linear. It's linear plus a quadratic term.
Yeah.
Technically, there are also some truncation which further exacerbates the problem. And because this Q function lies in a weird function class, and this guy can be written as exponential of those exponential sum of those Q functions, it seems to us very challenging to control the class of this V function. This is where we got stuck in the proof.
So here's an idea. Actually, I think it's Gergo and Kyoto together. They said that like, oh, like it's so complicated sometimes that we have the action value function which is linearly parameterized. Why don't we assume that the value function is linearly parameterized? But I guess this is not really a value function here. That's the challenge. That assumption wouldn't have here.
Well, yeah, that's not exactly what we do. We still parameterize the Q functions in the end. Yeah, even though we only have state features.
Yeah, one reading of your paper is that like you're okay, like let's really care about the value functions, not the state action value functions. Yeah. Anyways, that's a different discussion maybe.
Yeah, it is totally a different discussion.
Okay.
So now I'm convinced that this is really hard because you really need to like cover this entire sum of Q functions, right? And that can really blow things up.
Not that bad. That on its own is not bad, but like that you have the bonus, and you also have this projection with the policies, which are the softmax things. It's like altogether, it's a little bit wide. Do you have a guess of like whether this is a temporary difficulty that we can eventually overcome, or is it is there an underlying impossibility result hiding here somewhere that like this space doesn't have a nice small covering number?
Wow. I don't know. Honestly, I'm not sure.
Okay. All right.
It's in terms of impossibility result, it seems also very hard to establish.
Yeah, I mean, yeah. Like, how big is this space?
The main challenge of showing this is that the function class where this QHT belongs to is not a linear space. Yeah. If we add those two Q functions together, it's not the Q function anymore. Because it's a linear plus square root of quadratic. The bonuses are killing all of this. Yeah. So that means we cannot control what's inside of the exponential function for the policy. We don't even know what kind of policy class it is. It's different from, say, parameterizing using softmax parameterization. That would be much nicer.
Yep.
So in the chat, Sharon had a question about computational efficiency. Maybe you can ask a question if you're around.
Hi. So I noticed there was like a sum across the states to generate like this phi of v. So is this necessary like in every iteration? Do you need a pass over the states? Yeah, like this one.
Oh, yes, it is necessary because we need to compute. We need to compute the Bellman equation associated with the estimated parameter. That is, we need to compute this term, and under the linear kernel MDP, to compute this term, we need to compute sum over the states.
Right, but in the linear MDP, this won't be necessary, I guess.
Yes, because here the model is slightly different from the linear MDP.
Okay.
Yeah, it's a parametric model. We directly parameterize the transition model itself, but in linear MDP, well, I think they implicitly parameterize the model class.
Can I ask a related question?
Yeah.
So maybe maybe it's an additional restriction or something on this kernel phi, but maybe you could assume something that you can sample the S prime, and then you have a generative, I don't know, model underlying the phi. So maybe the phi is really a probability kernel, and somehow like some sampling, although it's a multi-dimensional thing, so I don't know how that works. But yeah, like, have you thought about any sampling approaches to maybe at the price of additional assumptions on what phi could be to make this algorithm computationally tractable in large state spaces?
Oh, yeah, yes. I think. Oh, recently I read a paper by researchers in MSR, Kakaday and Wensun and their collaborators. They consider a RKHS model where the feature actually maps from the current state and action to S prime directly. They assume S prime itself lies in some Euclidean space. So in other words, they do not parameterize the transition probability. They parameterize the system dynamics.
Is that the lean Mangdi factored thing?
Yes, it's similar. Yes, I think in that view, it might be. We might be able to say something more about how to estimate how to obtain this term, because in that paper, their feature is not dependent on the value function anymore. So in other words, we can impose more model assumptions, and to make this computationally efficient. Otherwise, seen from this formula, it seems that we can only sample uniformly over the state space, or otherwise use some off-policy evaluation techniques, maybe.
Okay.
So yeah, I have a question. So currently you are dealing with this policy learning in the full information setting, and what if you are doing policy learning with partial information or banded feedback? I guess in that case, you still need to do some kind of covering argument, right?
Oh, it depends on I guess this is a very nice question. I guess if in the banded feedback setting, we can just estimate the reward function itself, And then we can construct, say, assuming the reward function is linear in another basis, then we can use another linear regression to solve the reward, to estimate the reward, and get some uncertainty quantification, and also add another bonus function. That is doable.
So I think you don't need to do covering, because I think the reason why linear kernel MDP works in this setting is because essentially you don't need to do any covering in your proof. But if you are using linear MDP, then you need to do covering, and because of the bonus function and also the softmax form of the policy, so the covering is a very nested process, and it's hard to get a reasonably small covering number. So because my original thinking is, if you want to deal with banded feedback, then you will encounter similar problems as you encountered in the linear MDP setting, that you still need to do a covering number-based argument, even under the linear kernel MDP setting. So have you thought about this, or you think this can be avoided by doing something you just described, using another bonus for the reward?
Well, I think in banded feedback, it's as long as we restrict ourselves to the linear kernel MDP setting, I don't think we need to cover. Maybe I'm wrong, but I don't think we need to have a covering number.
Because if you introduce an estimator for the reward, then you need to introduce another, like a sort of Q function, which is different from the Q hat or Qt you are using in your proof. Right? It's like a pseudo Q function based on the estimated reward. It's not the Q function based on the true reward.
But I think this is very similar to a banded problem, because here we pose some assumption on the transition kernel, and here we assume the reward function is known. But if the reward function is unknown, say assuming the transition kernel is known, in that case the problem is only for learning the reward.
Yeah. If the transition kernel is known, then you don't need to do covering even in the banded feedback setting. But if the transition kernel is unknown, then I think there's still some dependency issue that you need to sort out. Otherwise, I didn't carefully track the proof, but that's my impression. If you need to deal with banded feedback, the proof will be much more challenging.
Okay, thanks for the question.
Yeah, we can discuss offline. Yeah. Just curious whether you thought about this problem or not. Yeah. Thank you.
Thank you.